At this point in the story, I have designed, built, and competed with my Omnidrive combat robot named Scale with some success. The drivetrain proved valuable, HDP chassis is durable, and general electronics worked fine, but the robot had several flaws to be addressed. Some minor things like increasing speed, but other much more major, like an entirely new construction, and importantly, a truly destructive weapon. It had been a bit over a year since I first built Scale Mark 1, and it was time to put what I've learned since then into practice. This video covers the changes I've made for Mark 2, actually implementing those changes with new machining techniques, and the result of all that work at the most recent Robot Havoc event. A quick recap of the main feature that makes this machine special is its holonomic drivetrain. It essentially means it can move in any direction without the constraints that tank or car steering has. Commonly seen in first robotics, the theoretical advantages is being able to outmaneuver opponents for unique attack angles, since robots are predominantly tank steer. I choose to go with the 3-wheel kilo drive, or Kiwi drive, for its simplicity. Based on an old photo from the Robots combat tutorial book, the final design was an invertible drum spinner. This robot was built and taken to 2 events where it eventually got 3rd place at Robot Havoc 5. It's a pretty good result, but the robot had some clear weaknesses. While manoeuvrable, it wasn't very fast and couldn't keep up with some opponents. The chassis was made of 3 pieces stacked on top of each other, which meant there was a loss of strength between the layers. But most importantly, the weapon was ineffectual and never caused any real damage. A ton of weight was spare in Mark 1, so there was heaps of room to rework things, and the side goal was also to reduce the size of the robot even further. Addressing that first problem, to increase the speed, one can either increase the wheel diameter, increase the motor speed, or reduce the gear reduction. More volts wasn't an option, as the whole robot was already running at the limit for the rest of its electronics. Bigger wheels would change the whole design of the robot, and is trending away from the goal of smaller, so I didn't go with that one. Faster motors would be the easiest drop-in replacement, as like many drone motors they come in a variety of kV ratings. This is a relationship between RPM and voltage, determined experimentally, so 100 kV means 100 RPM per volt applied with no load. While this is the easiest, the motors are 40 Australian dollars a piece, so replacing 3 of them plus spares was a cost I'd rather not spend at the moment. So on the gearboxes, I chose to construct my own. For simplicity, a single reduction spur gearbox was the goal. Currently it was geared for 9.6 to 1 with the old gearboxes, so I aimed for roughly double the speed with a target of 5 to 1. Turns out blank gears are pretty cheap from China at this size range, so I was able to pick up what worked best. Module 1 11-tooth pinion gears could be gotten for pretty cheap, with an inner diameter that press fits nicely onto the existing motors, so the size of the gears were pretty much set. The biggest gear that would fit within the 30mm height of the chassis was a 55-tooth gear, so that was also pretty much chosen for me as well. Cheap ball bearings would support the output shaft, which is an 8mm piece of hex, so it would natively fit the Omni wheel. Mark 1 used brass shafts, but turns out that titanium hex is quite cheap. It was a no-brainer to switch to that for a stronger and lighter shaft. Aluminium plates would frame the gearbox with printed ABS spacers. Making the aluminium plates was quite straightforward, though the first plates bent from the dry forces so had to be remachined with less pocketing later on. Titanium axles were a pain to make, as with any titanium part. Turning it was fine, but drilling without the perfect speeds ruined the draw bits, so business as usual for titanium. The gears needed a triangular feature to engage with the hex, and it had to be machined as centrally as possible, otherwise the gear would wobble on the shaft. Using some scrap aluminium, I milled a hole and creeped up on the perfect outer diameter of the gear so it would fit snugly. Some screws to keep it retained, and now I had a feature machined with the spot on the perfect centre already set as the machine zero. It was then easy to smash out a few gears, and the gearboxes were assembled. Onto the chassis, this new one had to be stronger than before while avoiding the layered approach. That was done previously because I was unable to machine multiple setups accurately, but that restriction had since been lifted. Keeping the same general dimensions, a single piece of 30mm HDPE would be used. HDPE that thick was very hard to come by in Australia, with only a single supplier selling it. It seems that 25mm is the upper limit of easily available stock if you're looking to make your own. In designing this new version, it is worth considering how the armour was placed on Mark I. I was moving away from aluminium armour panels, as straight HDPE seems to work better, so some parts of the chassis had to be thicker than others to accommodate ablation. Taking a look at the damage on Mark I, it was almost exclusively on the front end and just around the front wheel pods, so material was biased that way. A bit of a gamble, and for aesthetics, it received wings to extend the front armour face further back to keep impacts away from the middle of the chassis where all the electronics and expensive bits are stored. This had the disadvantage of giving an edge for weapons to catch on, but I decided it was worth the trade-off. Due to the new offset gearboxes, the whole robot could be shrunk a little as components moved to more optimal positions. Machining the chassis on my mill took a few setups to get done. Using a big 2-flute cutter, I removed the majority of the material very quickly, and a smaller single-flute tool got the smaller details. The chamfer tool had a chipped tooth, which meant suboptimal finish, but it did get the job done. The 3-axis milling machine, such as what I've got, can only machine what's visible when looking top-down, so the chassis had to be flipped for underside features. The challenge when moving a part around like this is telling the machine where it is in space accurately. Errors can compound here. Maybe the part isn't perfectly the same dimensions as the CAD model. The plastic might be a bit flexible and a minutely different shape when clamped down. A part has to be positioned super squarely to the machine bed, or a feature maybe far away might be different to where you think it is when the measurements are off, and many other factors. Even if one error only introduces 0.1mm deviation, a combination of 5 other errors leads to about half a millimeter difference from what it expects, which is a chasm in a part like this. As a result, one minimises the number of times the part has to be moved, and takes steps to indicate off features on the part that are known square, even adjusting the CAD model when you measure it for the actual dimensions. In the end, the chassis came out quite well. This was my first multi-setup part. I was quite happy with how it turned out. Compared to machining the weapon though, this is quite an easy job, and that's the next bit of the robot we need to tackle. I keep harping on about needing a bigger weapon, so it was time to actually design one. I knew this immediately after the Adelaide competition, so I had knocked out a concept while waiting for the plane home. It was about around this time that the battlebot Omnidirectional had been named over to the public, so I experimented with a similar weapon concept. But it's worth discussing what actually makes a good weapon first. In engineering, good is an extraordinarily dependent term on the use case. For us here, it's the maximisation of damage while fitting certain design parameters. Our design parameters are a mass of 300 grams, had to fit between the front wheels of the robot, had to use a hub motor to power it, had to be machinable on a 3-axis mill, had to be affordable, and strong enough to survive Beetleweight combat. Some of these parameters are a bit subjective, so the goal would be to achieve all of them to as high a degree as possible, that is without much trade-offs. In regards to damage, there are 2 metrics to consider: stored kinetic energy and bite. Stored kinetic energy is a property of rotational speed and moment of inertia. Moment of inertia, the metric of momentum when spinning, goes up to the square of radius in this case. Doubling the radius would quadruple the stored energy with all else being equal. Old scale was invertible with its small drum, but this design feature would have to go. Doubling the effective outer diameter was chosen. Not all shapes are equal in moment of inertia though. A cylinder has roughly half the moment of inertia of a thin hoop of the same length and material, as the matter is concentrated further out. A disc type, as seen on Omnidirectional, arguably leaves some energy on the table with all that dead space that could have had the centrally located material moved outwards. This is not a new idea. Such a weapon is typically known as an eggbeater, and it's perhaps the most common weapon type in this Beetleweight weight class due to the proliferation of fingertex variant. It aims to be as hoop-like as possible, but has the disadvantage of being pretty hard to make as well as being weaker. Cutting an Omnidirectional style disc is very easy, it's just a 2D profile, but an eggbeater needs 3D features to work. Nonetheless, it is possible to machine on a 3-axis mill, so our new weapon would be of the eggbeater variant. Our second kinetic energy factor, rotational speed, It's pretty simple. The faster it spins and the more energy it stores. The kinetic energy actually goes up with the square of velocity, so double the RPMs means quadruple the kinetic energy. Keeping the same form factor motor as before, I picked out the highest speed variant available, which had 2.5 times the kV. This, combined with the increased diameter and weight, means we have a theoretical peak energy storage of about 62 times the old drum, which is quite a significant margin. Now, it's all good to store big joules, but that's only half the battle. Delivering the energy is a whole other ballgame. Robot builders use this metric byte a lot, which doesn't really exist, but it's very similar to the machining term feed rate. When milling some material, the cutter advances a certain distance every rotation of the tool. Depending on how many teeth the tool has, this leads to some advanced distance per cutting edge. Combat robot weapon impacts follow the same theory, some rotational speed and number of teeth being advanced into the opponent at a certain speed. In our case, though, our feed range needs to maximise how much the tooth bites, while not being too much to go beyond the depth of the tooth. This is why some fast drum spinners grind instead of biting. There isn't enough feed rate for tooth engagement for the RPMs. One can math out optimal factors for everything, but I only wanted to consider the number of cutters here. The fewer the number of cutting teeth, the more engagement one gets, all else being equal. This is why most modern weapon designs have only a single tooth. Even the fingertech bar has offset impactors to accommodate this. The disadvantage to a single tooth weapon is complexity in design, for it not being naturally balanced shape, and the raised potential for a fast hit to go beyond the tooth depth. My ring spinner uses 2 teeth for this reason. Many hits would engage the old single-tooth weapon's counterweight instead of the teeth. For designing at scales beater, I was confident in the single-tooth approach, as RPMs were so high I wasn't worried. The final design parameter was to make the beater out of 4140 steel, strong enough to survive hits but also cheap and relatively easy to machine. Knocking out the CAD work produced this model. Using the same bearings as the old drum, this beater looks significantly better than the old drum with a deep tooth and heaps of distance between the delicate motor and the impacting surface, which is good since the old drum failed when the motor was caved in. Curling the tooth for a negative rate angle meant it should pull material as it bites, where a positive angle pushes it away. A quick mention of how the weapon is mounted into the chassis. The old drum used bent 3mm aluminium plates nestled in cutouts. These are pretty weak, and it basically failed by the time Mark I was retired. The new design used a pair of 10mm chunks that rest on a large piece of the chassis, with all weapon loading being in shear or compression, rather than bending the weird plates over like previously. This is significantly better. Time for the tough bit, actually making the weapon. 4140 comes in round bar stock, so a section had to be cut off and milled into a usable rectangular shape. Trying to part the stock in my lathe did not end well. A parting tool exploded in perhaps the loudest way possible, so I had to finish the cut with a hacksaw, and the part was then put into the mill for facing. Going back to indicating when doing multiple setups, the vise had to be perfectly square and parallel to the machine as possible, as any error here will be seen in every single cut taken afterwards. There is a particular technique for making square blocks that relies on trusting certain vise faces to be square and perpendicular, then passing the squareness and perpendicularity onto the part with each cut. In the end, one gets a pretty square block. It takes some time on such a small mill as mine though. The beater was designed to be machined in 4 setups, holes and bores in each end, and then top-down profile machining, and then the underside. Bores were done first, as once the beater profile is machined, it becomes very difficult to realign it to the machine accurately, as all external surfaces are weird shapes. After doing the bores, I went to mill out the big pocket in the middle of the beater. The machine tried to cut with full tool width, and completely locked up, so I had to restart. It was a little while later that I realised this lockup caused the machine to lose steps, where there are given movement commands that can't be carried out, but the controller goes on anyway without knowing the movement was not carried out. Without re-indicating the machine, this means that the pocketed feature was offset by about 8mm in X and Y, ruining the part. A new bit of stock was then cut off, squared again, rebored, and it was back to pocketing. This time things went a lot better. Top features were machined successfully. A ball end mill finished the curvy contours. A flat end mill cannot do curved surfaces, so one has to use a round one. The mill spindle casing was resonating due to the cutting forces backing up the machine, so so I was definitely getting up to the high end of what such a mill can do, but stuffing a socket between the case and the frame seemed to help things a lot. Setup 3 seemed successful, so it was time for the final cut. Roughing and finishing went well, and we have ourselves a pretty mean looking beater bar. The robot was then all assembled and wired up for testing. The design flaw became obvious pretty much immediately. Due to the massive front-mounted weapon, the rear wheel had effectively zero weight on it, which means it had no influence over driving. Thus the robot lost its ability to strafe, which was the entire point of OmniDrive. I had about 100 grams to spare at this point, so I taped some mass to the rear, and that seemed to fix things. Later, Scale Mark II would gain some rear steel armour to balance things out. Finally, it was time for a weapon test. Things were sounding good, but one issue had yet to be addressed. The robot was no longer invertible. I had hoped the weapon had the torque to spin up and flip itself over. This was not the case. Thus, Scale gained ears. The beater pushed so much air that it could pull itself along the ground on that alone, and using the rear wheel to steer, it could still engage an opponent, or it could try to flip itself back over. Forks were another point of development. Initially, 4 little aluminium ones were used, but these would bounce up and down ineffectually when the weapon was spinning. After much testing, long steel forks with some elastic elements completely negated this. I used O-rings for the elastics. With the event rapidly approaching, some quick weapon hits were made. From this slow motion shot, it seems like the beater is delivering all its energy quite well, as after the hit it's barely spinning. Unfortunately, I also found that I could only run full weapon power for about 20 seconds at a time without the motor overheating, though about 50% seemed quite fully sustainable. I think this would just be in part due to how aerodynamically inefficient the weapon is, but there's no time to fix that. 1 year after the last one, it was time again to attend Robot Havoc in Adelaide and see how Mark II fares. This Robot Havoc was similarly busy to the last one, as I brought 4 robots, though this gained me some extra pit space. Many familiar builders there, and we were now competing Beetles in the proper arena rather than just sectioning off part of the feather box. Scale would have 4 round-robin fights before hopefully entering the finals if it got enough points. The first match was against Alba X, a 4-wheel drive pusher with entrapping wings that can snap forward to control opponents. The Adelaide arenas are, for a lack of a better term, very pitty. 2 pits would open after 60 seconds, which were very centrally located, and since it was very hard to avoid them. Even Alba X would be trying to get under me, I went fork to try and get under them. The fight starts with me holding just under half weapon throttle to maintain control, and Alba X immediately has a good grab and push. Their beak gets caught in the beater though, throwing them backwards. After a little shoving back and forth, Scale gets another good grab, which throws them backwards and into the wall. I conferred with the other driver, and they said that I could attempt to get them back down, but when they hit the ground it was clear that they weren't working anymore. This was a good first win for Scale. The damage on Alba X was a bent-in beak, some electrical fault, and some pretty ruinous damage on their thin aluminium top plates. Second fight was against Unmaker, built by the ever-expressive Chris McKee. Unmaker was a 4-wheel drive vertical spinner with some ground game of its own. The angled wedges could prove hard for the beater to get a bite onto. The fight starts and we're both cautious of each other, each being new robots and unsure of how we take damage. Unmaker moves in for an attack, and Scale just about strafes sideways, gets around and pulls a wheel off. It seems Unmaker has lost motion, but it once again retains movement. Scale then gets a good bite on the underside of the wedge, and throws Unmaker corner to corner, thanks to the fork getting under the panels. At this point, Unmaker is counted out. For this fight, it was good to see some good quick damage, and the use of the OmniDrive, but it was unfortunate as Unmaker was having intermittent drive the whole event. Should get a rematch eventually though, and we'll see how things pan out. Chris has a YouTube channel as well, with some footage of testing Unmaker and all the prototypes. it could be worth a look. The third fight was against Hissy Fit, a robot built by another Sydney builder named Matt. A fairly standard Fingertech beta bar with an all-enclosing HDP chassis, so it should be pretty hard to kill. I didn't see a reason to risk running forks for this match, so I removed them. For some reason, I drove very cautiously with very little weapon throttle, about 30%. Still not sure why. The fight starts and I advance towards them, soon knocking them into a wall, which somehow breaks their weapon belt. Most of the match was then me cautiously chasing them down and tapping them with the weapon, but not doing much to their very durable chassis. Once the second pit is able to drop though, I shake off the sleepy attitude and go in for a proper hit. This fire put a hold on the event while the smoke cleared out, giving some time to mull over what happened. Turns out someone happened to be doing a super slow motion shot at just the right time, so we can actually see what went down here. A combination of previous damage and the inertia of the heavy battery meant that when scale hit their rear top plate, it gave way and the LiPo fell out. The robot then fell down with the LiPo landing on top of my beater, which pierced it. This caused a proper fire that scorched the floor and most of Hissy Fit. But no time to consider that anymore, as the final round robin fight was against Iron Tooth, a big horizontal bar spinner. Their weapon is actually longer than scale is wide by a significant margin, and this was the fight that I was dreading for the whole event. Up until this point, scale was scratch-free, having dispatched opponents pretty swiftly, so I had no idea how it would hold up against such a big weapon. Again, no forks, as it'd only be a hindrance here, and the fight starts, and I box rush Iron Tooth, catching their bar before it spins up. It just about roofs them and breaks their weapon motor pulley clean off somehow, as the motor's buried pretty deep into the robot. They're down a weapon, but they're not out, and they're still able to push, and with the pits opening soon. I spent the next minute tossing them around and removing tyre tread. Once the pit opens up, I'm just able to outpush a treadless Iron Tooth into the pit for a 4th round robin win. Now in the quarterfinals, Scale was up against Hurt Feelings. This was a well-built undercutter, much like the machine that took out Scale last time. I'll let this one play out as there was a bit too much happening to talk over.
Fight.
He's gone for it. Back, James. Back to that bit. Oh! I really can't afford to zoom in on this. Get him, James. Get him.
An unfortunate loss, but a good fight nonetheless. Scale seemed to struggle with drive at the end as a screw had backed out from the weapon uprights, meaning that one wheel was off the ground. But otherwise, Scale and Hurt Feelings left that match fully functional, so it was a bit disappointing to lose such a match by pitting. Some of the drive wheel's gear had been ground off on Hurt Feelings, so we were both just about starting to fill the match. Scale took the hits well, but seemed to be most stable upside down, which is unfortunate. Due to the weapon gyro, it was very hard to turn while inverted as well. This meant that Scale was knocked out of the bracket to have some fun in the rumble, which it just about won. Its second loss for the event, though, was the weapon, which died a bit into this match. The weapon axle had bent, which caused the weapon motor rotor to hit the stator and spin the iron on its post, which sheared the phase wires and killed the weapon pretty dead. So that's what Scale Mark II is up to at this point. Apart from needing a thicker weapon axle, it's almost just waiting for the next event. The weapon uprights bent a little when fighting the undercutter, but this can be rectified pretty easily by unpocketing them. The drive gearboxes worked well, but the metric 2 bolts holding them together sort of widened their holes, which caused some looseness. Billet version will be coming next. As far for improving the weapon, I think things went a lot better, as 3 of the 4 wins were by a pretty decisive knockout, and the 4th being a pretty decisive pitting. A part of the eggbeater tooth got smooshed a bit, and it just cleaved its way through the chassis, and aluminium uprights no problem, so there's clearly enough energy here. Due to being much more aggressive, the Omni drive didn't play as large a role as before, but still worthwhile in my opinion. We're aiming to host a Beetle event in Wollongong soon, so Scale should fight sooner than the next Adelaide event. Now that I intend to make videos about things, we should have better footage for that one too. In the next video, I plan to talk about another ant weight of mine called Split that uses the eggbeater lessons from this robot and applies them to the ant weight scale. Until next time.
Flip side from the ring spinner, right?
Well, that's cooked.
Holy crap.
Get the super glue. Yeah, that'll buff out. That'll buff right out. Oh my god.